Welcome to the deep dive. We're jumping straight into something that's really changing how we think about predicting the future in economics and finance. For years, we've often looked at single best guesses, or maybe simple measures of risk. But what if we could understand the full range of possibilities, from the most optimistic to the most pessimistic, and crucially, how likely each one actually is?
That's exactly it. I mean, traditional forecasting methods, they're useful, sure, but they often struggle. They really struggle with the messy reality of economic and financial data.
Yeah, like those standard models assuming nice bell curves.
Right. And think about those sudden market crashes or unexpected booms. They don't always fit neatly into those standard statistical boxes. Plus, we're now swimming in just vast oceans of data. Older techniques weren't really built to pull meaningful insights from that kind of volume and, frankly, complexity.
Exactly. And that brings us neatly to the paper we're digging into today, Learning Probability Distributions in Macroeconomics and Finance. The authors explore a really powerful new approach using deep learning, specifically recurrent neural networks. So instead of just predicting one number, they're aiming to forecast the entire probability distribution. It's kind of like upgrading from a blurry snapshot to a detailed panorama of what might happen.
And the implications are, well, potentially huge. Imagine being able to more accurately gauge the real risks in financial markets, or just having a clearer picture of the potential range for economic growth, for instance. This isn't just theory. It has real-world consequences for investors, policymakers, businesses, everyone making decisions under uncertainty.
Okay, so today we'll focus on how these advanced machine learning methods tackle the shortcomings of traditional forecasting. Specifically, we'll look at creating macroeconomic fan charts using massive data sets and also predicting the conditional distributions of asset returns, which sounds very relevant for, say, designing trading strategies.
Absolutely. Understanding that full distribution is key for risk management, which is foundational for any sound strategy.
Okay, let's unpack the why. Why this big shift towards probabilistic forecasting? Why is it so critical now to move beyond just point estimates?
Well, think about making any important decision. Maybe it's a central bank setting interest rates, or even just someone planning for retirement. If you only have one prediction and maybe a vague idea of the risks, you're sort of flying blind, aren't you?
Hmm.
Probabilistic forecasting gives you a much, much richer understanding of the landscape of possibilities. So, for example, a point estimate might suggest, say, moderate economic growth. But the probability distribution might actually reveal a significant non-trivial chance of a recession lurking there.
Ah.
That extra information is just vital for making properly informed choices and, crucially, managing potential risks effectively.
So how does this deep learning approach really differ fundamentally from the more established ways economists have tried to forecast distributions, like, traditional time series models or surveys?
Right. So traditionally, we've often built models based on, let's say, predefined assumptions about how economic variables interact. It's kind of like having a rigid blueprint that dictates all the relationships.
Okay.
Deep learning, on the other hand, is more like letting the data itself draw the blueprint. These networks, they can learn incredibly complex, nonlinear patterns directly from the historical data. And
Right.
we don't have to explicitly specify all those underlying relationships beforehand, which is a big advantage.
And surveys.
Surveys capture opinions, which are definitely valuable, but they don't necessarily reflect the intricate statistical patterns that might be hidden deep within the data itself.
We've seen machine learning get really popular for making single point predictions, right? Especially in economics and finance. This paper argues probabilistic forecasting is the natural next step. What makes it such a big leap forward?
Yeah, machine learning has definitely proven it can find subtle signals
Yeah.
in huge data sets to make often very accurate single predictions. But in so many real-world scenarios, the uncertainty around those predictions is just as important, maybe even more so.
Right.
Knowing the range of possible outcomes and their likelihoods allows for much better risk management, more robust decision-making. It feeds directly into things like portfolio construction or hedging. The innovation in this paper is developing a specific strategy using deep learning, particularly these recurrent neural networks, to directly forecast the entire probability distribution. And they do it in complex high-dimensional settings without needing to build a rigid, pre-specified model first.
Now, the paper does point out some real hurdles. Forecasting economic variables probabilistically isn't easy. Things like distributions that aren't nice bell shapes, the fact that relationships change over time, those unpredictable spikes, sudden shifts. How does this new method try to tackle all that?
Exactly. Economic data can be pretty unruly. It often has fat tails, meaning extreme events happen more often than a normal distribution would suggest.
Yeah. Right, like market crashes.
Precisely. And it can be skewed where, say, positive surprises and negative surprises have different probabilities or different impacts. Traditional models often really struggle to capture these nuances. Deep learning models, because they are essentially universal function approximators, have the potential to learn these complex shapes, and they can adapt to changing patterns in the data much more flexibly.
So they learn the rules from the data itself.
Pretty much, even if those rules are complex, nonlinear, and maybe even changing over time.
The paper also contrasts their method with traditional ways of looking at asset return distributions, like conditional quantiles or distributional regressions. What are the limits of those older techniques, especially with lots of data?
Yeah, those methods often rely on quite strong preset assumptions about the mathematical form of the relationships they're trying to model. When you're in a high-dimensional setting, with potentially hundreds of factors influencing returns, these assumptions can just be too restrictive. They might not capture the true complexity. They might also struggle to model how the entire shape of the return distribution changes under different market conditions, which is critical for risk assessment.
This brings us to the star of the show, as you mentioned, distributional neural networks, or DISTRNN. What exactly are these things? How do they approximate these probability functions?
Okay, imagine trying to describe the chance of different temperatures tomorrow. Instead of just saying it'll be 25 degrees, you might say, okay, there's a 10% chance it's below 20, a 50% chance it's below 25, a 90% chance it's below 30, and so on.
Uh-huh.
A DIST-RNN works in a similar way, but for economic or financial variables. It's a special type of neural network specifically designed to output these probabilities for a whole range of different possible values. So it effectively learns the entire conditional probability distribution, not just a single point.
And how does it do that? You mentioned feed-forward neural networks being universal approximators. Can you break that down a bit?
Yeah, think of a feed-forward neural network like a very, very flexible function. Given enough data and the right structure, the right number of layers and nodes, it can theoretically learn to approximate almost any relationship between inputs and outputs, no matter how complex or nonlinear.
Wow, okay.
DIST-RNN really leverages this power. Instead of us telling the network, okay, the distribution follows this specific mathematical formula, we just give it the data, and it learns that relationship directly. It's kind of like teaching a child to recognize different animals by showing them loads of pictures, rather than giving them a strict set of rules for what defines a cat versus a dog.
Got it. So the network takes in predictors, maybe past returns, volatility measures, macroeconomic indicators,
Right, a whole set of inputs.
and then it jointly models the probabilities for different quantiles, those 10%, 50%, 90% points of the future distribution. How does that actually happen inside the network? What are these hidden layers and activation functions doing?
Okay, so the input data are predictors. They feed into the first layer. Then they pass through one or more hidden layers. In each hidden layer, the data gets transformed. It goes through a series of weighted connections, like adjusting knobs, and these crucial nonlinear activation functions.
Linear.
Because that's what allows the network to learn complex, non-straight line relationships. If everything was linear, you could just collapse it all down to one simple layer. Think of an activation function like a dimmer switch or maybe a gatekeeper, deciding how much of a signal gets passed on to the next layer.
Okay.
By stacking these layers and using these nonlinear switches, the network can learn incredibly intricate patterns. Then, the final output layer is structured to give us those estimated probabilities for our chosen quantiles.
Now, for time series data, which is most economic and financial data, the paper emphasizes recurrent neural networks, RNNs. Why are these better suited than standard feed-forward networks?
The key difference is memory. RNNs have a built-in mechanism to remember past information. They process sequences. Think about predicting the next word in this sentence. You need to remember the words that came before, right?
Right. Context matters.
Exactly.
Yeah.
RNNs work similarly with time series data. They can capture temporal dependencies, how past values influence future values. Feed-forward networks, they basically treat each data point independently. No memory of the sequence.
And within RNNs, they specifically mention long short-term memory networks, LSTMs. What's special about LSTMs for capturing those long-term dynamics we often see in economic cycles or financial markets?
So basic RNNs can sometimes struggle with remembering information over very long periods. Their memory can fade effectively. LSTMs were designed to overcome this vanishing gradient problem. They have these special components called memory cells and gates specifically. Input gates, forget gates, and output gates.
Gates, like controllers.
Sort of, yeah. These gates act like regulators. They allow the LSTM to selectively store important information over extended time periods, and also to decide when to update or discard old information that's no longer relevant.
Ah, clever.
This makes them much, much better at capturing long-range dependencies in the data, which is often absolutely critical for understanding things like economic cycles or long-term trends in finance.
So how does the network actually learn? How does it get good at producing these probability forecasts? The paper mentions a specific loss function. What's that doing?
The loss function is basically the teacher. It tells the network how wrong its predictions are during the training phase. It's a mathematical way to measure the difference between the network's predicted probabilities and what actually happened.
Okay.
The distort NN uses a clever combination. One part is similar to what's used in, say, classification problems. It encourages the predicted probabilities for each quantile to line up with the true probability of the variable falling below that quantile. But the other key part is a monotonicity penalty.
Monotonicity, meaning?
Meaning it has to go in one direction. The probability of being below a higher value must always be greater than or equal to the probability of being below a lower value. You can't have a 50% chance of being below 10 and only a 40% chance of being below 20, right?
Yeah, that wouldn't make sense for a cumulative distribution.
Exactly. This penalty pushes the network to learn a properly behaved, non-decreasing cumulative probability distribution.
Makes sense. Before we see this in action, can you briefly touch on the practical side? Designing and training these networks, what are the key steps?
Sure. They use sophisticated optimization algorithms, things like ADAM or ADAM-W, to efficiently adjust all those internal network weights during training, aiming to minimize that loss function we just talked about. Finding the right network structure and settings, the jargon, is hyperparameters, things like learning rate, network depth, etc. That's crucial. They often use techniques like random search to explore lots of different possibilities.
And you mentioned activation functions.
Yeah, they typically use something called ReLU in the hidden layers. And they also use a technique called early stopping that prevents the network from memorizing the training data too well, which would make it perform badly on new, unseen data. It helps the model generalize.
Okay, super interesting. Let's see how this actually works in the real world now. The first application they look at is creating macroeconomic fan charts using big data. We've seen these from central banks like the Bank of England. What are they exactly, and why are they useful?
Right. Those fan charts are basically a visual tool for communicating uncertainty around economic forecasts. Instead of just showing a single line for, say, the most likely path of GDP growth.
You see those shaded bands.
Exactly. You see a series of shaded bands, or fans, that typically widen as you look further into the future. Each band represents a different probability level, like the central 50% range, the 90% range. Gives you a visual sense of the range of possible outcomes and how likely they are. The wider the fan, the greater the uncertainty. It's really valuable for policymakers and the public to grasp the risks involved.
And the authors here set out to build these fan charts using deep learning, but on a massive data set, 216 variables. How does that compare to traditional methods?
Traditionally, fan charts were often based on more standard microeconomic models. These typically used a much smaller set of core variables and relied on more structured, predefined relationships based on economic theory.
So more theory-driven.
More theory-driven, yes. The deep learning approach here is much more data-driven. It aims to learn the underlying patterns of uncertainty directly from this vast amount of information without us having to explicitly tell it which variables matter most or exactly how they interact. The hope is that the resulting fan charts can potentially capture more complex and maybe more realistic aspects of economic uncertainty.
Tell us about this data set, 216 quarterly U.S. indicators. Sounds comprehensive.
It is. They use the FRWQD dataset, which is a well-known and widely used resource in empirical macroeconomics. It's got a huge range of quarterly data, national income, labor market stats, prices, interest rates, financial indicators, stretching back decades.
And they had to process it first.
Yeah, because many economic time series have trends or seasonality or their volatility changes over time. The researchers applied standard transformations like taking differences or growth rates to make the data more statistically well-behaved, more suitable for modeling.
Okay. And how did they actually use their dist-RNN framework to get the forecasts needed for these fan charts, looking several quarters ahead?
They use what's called a direct prediction scheme, which basically means they trained separate dist-RN models for each forecast horizon they cared about.
So one model for 1 quarter ahead, another for 2 quarters.
Exactly, up to 6 quarters ahead in their case. Then, to get the smooth, continuous probability distributions needed for the fan charts from the network's specific quantile predictions. They used a mathematical technique.
Interpolation.
Right, specifically Frisch-Carlson monotonic cubic interpolation. It essentially draws a smooth, sensible curve through the predicted probability points, ensuring it looks like a proper cumulative distribution function. From that smooth curve, they could then easily calculate the prediction intervals, the bands, for different probability levels, like 50%, 90%, that form the fan.
Now, to see how well their method worked, they needed a comparison. They used a Bayesian vector autoregression, a BVAR model. Why that specific benchmark?
The BVAR is a pretty sophisticated and commonly used statistical model in macro forecasting. The B for Bayesian means it allows incorporating some prior beliefs, which can help, especially with lots of variables. And the specific BVAR they used also included factor components, which helps it handle a relatively large number of variables, not quite the 216 the dist-NN used directly, but it could summarize the information from them. So it's a strong, relevant benchmark.
And how does the BVAR typically handle uncertainty?
Crucially, the BVAR model usually makes an assumption about the forecast errors, often assuming they follow a normal bell-shaped distribution. That assumption directly shapes how its prediction intervals are calculated. The dist-NN doesn't make that assumption.
Gotcha. And how did they actually compare the forecasts? How did they evaluate which method was better probabilistically?
They used a metric called the quantile loss function. Think of it as a way to measure accuracy not just at the center prediction, but across the entire predicted distribution at different quantiles.
So it penalizes errors differently depending on whether you're predicting the tails or the middle.
Exactly, which is critical when you're evaluating the whole distribution shape. They set up a rigorous test defining forecast horizons, probability levels for the fans, and using a growing window approach.
Meaning they retrained the models as more data came in.
Yes, standard practice for evaluating time series forecasts realistically. They also carefully tuned the hyperparameters of their deep learning model through optimization to make sure it was giving its best shot.
So what did the results look like? Comparing the fan charts from dist-NN versus the BVAR for things like GDP, inflation, unemployment, any visible differences?
Visually, yeah, there were differences. The fan charts from the deep learning model often looked, well, less smooth and showed more asymmetry compared to the BVAR charts.
Asymmetry, meaning the upside and downside risks weren't necessarily equal.
Precisely, suggesting the dist-NN might have been capturing more complex aspects of the uncertainty, perhaps reflecting skewed distributions of future outcomes. In some cases, the dist-NN intervals were also narrower, maybe indicating more precise uncertainty estimates.
Interesting.
And they noted the BVAR seemed to struggle a bit more with capturing the changing uncertainty around the unemployment rate compared to the dist-NN.
Okay, that's the visual. What about the quantitative results, those quantile loss numbers?
The numbers generally backed up the visuals. The distributional recurrent neural network, the dist-NN, showed lower quantile loss, meaning better accuracy across most forecast horizons and most probability levels. It did particularly well for shorter-term forecasts and for those wider 90% prediction intervals, suggesting it was better at capturing the tails.
Any exceptions?
Inflation was a bit more mixed. The results weren't as clear-cut there. But for GDP and unemployment, the dist-NN generally had the edge. They also used a formal statistical test, the Diebold-Mariano test, to check if the differences were statistically significant.
Yeah.
And it indicated that deep learning provided significantly better predictions in several instances, while the BVAR rarely significantly outperformed the dist-NN. They did add a caveat that the length of their out-of-sample test period was a bit short for this test to be perfectly conclusive, but the trend was clear.
That's really fascinating. It does suggest that deep learning can offer a more data-driven, potentially more accurate way to assess macroeconomic uncertainty by using much more information. Okay, let's switch gears to the second application, forecasting the conditional distributions of asset returns. Now, predicting stock prices is notoriously hard.
Extremely hard. The signal-to-noise ratio is very low.
So how does this approach tackle forecasting the entire distribution of returns, not just the direction or average?
You're right. Most research focuses on predicting the expected return or maybe volatility. There's much less work on forecasting the full range of possible returns and their probabilities. The authors do mention a relevant earlier study by Anatoliev and Barunik that used a specific statistical model of parameterized ordered logic for this purpose.
And the goal here was to see if machine learning could do better. Maybe by using more or different kinds of predictive information, could it find patterns missed by the logic model?
Exactly. They wanted to see if a more flexible machine learning model, specifically their dist-NN, could learn patterns from a richer set of input variables. and ultimately provide more accurate forecasts of the entire distribution of future stock returns, which again has direct implications for risk management and potentially for strategy design.
What kind of data did they use for the stocks?
They looked at daily returns for 29 of the most liquid stocks in the S&P 500 index, big names. The data ran from mid-2005 to late 2018, giving them over 3,000 daily observations per stock. And they did some standard pre-processing, adjusting for liquidity differences and removing holiday effects.
What predictors did they feed into their models for these stock returns?
They tried three sets. First, they used the same two predictors as the benchmark Anatoliev and Baranik's study, what they call the AB predictors. One was an indicator for past negative returns. The other was basically past volatility.
Okay, relatively simple inputs.
Right. Then they introduced a second set, derived from high-frequency, one-minute intraday data. These were realized measures, RM predictors. Things like realized volatility, realized skewness, realized kurtosis, and measures of positive versus negative price moves within the day. Much richer information.
And the third set?
Just combine both, AB plus
Yeah.
RM. And they made a really important point here. Trying to stuff all those extra RM predictors into the original ordered logic model would likely break it. Too many parameters, it would become over-parameterized.
So that really highlights a key advantage of the machine learning approach, right? Its ability to handle much higher dimensional input data without the same kind of constraints.
Precisely. It can potentially find useful signals in that high-frequency data that a traditional parametric model might struggle to incorporate effectively or at all.
How did they set up the training and testing for these stock return models?
Standard practice, mostly. They split the data into a training set, the first 90%, and a test set, the final 10%. For finding the best hyperparameters, they used a rolling window validation approach within the training data. They also used an ensemble method, basically training the best model configuration multiple times with slightly different starting points and averaging the results to make the predictions more stable and robust.
And things like early stopping.
Yes, early stopping to prevent overfitting. And they explored different network sizes, different numbers of hidden layers and neurons.
How did they measure performance here? Which model was doing better at forecasting the return distributions?
They used several standard metrics for probabilistic forecasts. I mean, squared prediction error, MSPE, which looks at the average squared error. Also, the continuous ranked probability score, CRPS, that's a really good one because it evaluates the accuracy across the entire predicted distribution in one go. And also the Breyer score, which is common for probability forecasts. To make comparisons easy, they reported the results as ratios relative to the benchmark AD model. So a ratio below 1 means the new model is better.
And what did they find? What were the key results for forecasting stock return distributions?
The overall takeaway was pretty clear. Machine learning, specifically their dist-NN, is definitely capable of forecasting the conditional distribution of asset returns quite well. And crucially, using more informative predictors, particularly those high-frequency realized measures, leads to better predictions. They saw average improvements around 1% in MSPE, which might sound small.
But you mentioned earlier, even small statistical gains can matter in finance.
Exactly. They referenced work suggesting even modest statistical improvements in return forecasting can translate into significant economic benefits for investors, better portfolio decisions, better risk control, things that are core to systematic trading. And the improvements in the CRPS metric were even larger, suggesting the shape of the predicted distribution was notably more accurate when using the richer data.
What happened when they ran the neural networks using only the original, simpler A-B predictors? Did the flexibility of the neural network help much then?
Interestingly, not really. When using just the A-B predictors, the neural networks performed very similarly to the original AD-ordered logit model. It suggests that the simpler parametric model was already doing a decent job of capturing the information in those two specific variables. The extra nonlinearity of the neural network didn't seem to add much value with those limited inputs.
But the story changed completely when they added the realized measures, the RM predictors.
Absolutely. That's where the machine learning approach really shone. Adding the RM predictors led to consistent and statistically significant improvements in forecasting performance across the board on all the metrics.
So confirming the idea that ML can leverage richer, higher dimensional data.
Yes. It really demonstrated the advantage of machine learning in handling that kind of information effectively, information that would likely choke a more traditional model. They also found, interestingly, that somewhat shallower networks, maybe just one hidden layer, tended to perform best in this specific application, which echoes some other findings in financial machine learning. Sometimes simpler is better, even with complex tools.
And did it work well for all stocks, or were there big differences?
Looking at individual stocks, the results varied a bit, as you'd expect. The ML approach showed particularly strong improvements for certain big names like Apple, Amazon, GE, Walmart. They also noted that sometimes the deeper networks, while not always having the absolute best average score, showed lower variation in performance across the different stocks, maybe suggesting a bit more robustness.
Okay, so let's try and wrap this up. Bringing it all together, what are the main takeaways from our deep dive into this paper on deep learning for probabilistic forecasting?
I think the central conclusion is pretty powerful. Deep learning techniques offer a really valuable, flexible toolkit for probabilistic forecasting, both in macroeconomics and finance, especially when we're dealing with data-rich environments, lots of variables, maybe high-frequency data, and when we suspect the underlying relationships are complex, nonlinear, and maybe even changing over time.
And the two applications we discussed really illustrated that point well, didn't they?
They really did. The macroeconomic fan charts showed how deep learning can potentially harness hundreds of diverse indicators to give a more purely data-driven picture of economic uncertainty, maybe capturing nuances missed by models based on fewer variables and stronger theory assumptions.
And the asset returns.
The asset return forecasting clearly demonstrated the potential for machine learning to incorporate richer data sources, like those high-frequency realized measures, to significantly improve our ability to predict the full distribution of future returns. That definitely outperforms traditional methods that either can't handle that data or make restrictive assumptions.
And as you highlighted, getting that full distribution right is pretty fundamental for sophisticated risk management and potentially for designing better trading algorithms.
Absolutely. It moves beyond just predicting the average outcome.
And the authors stress their distar N approach is quite general, right? Applicable beyond just these two examples.
Yes, that's a key point. It can be applied to many different forecasting problems without needing to make strong, often unrealistic assumptions about the specific mathematical form of the probability distributions involved. It's much more adaptable.
It really feels like a more data-centric way to understand and predict the whole spectrum of possibilities in economics and finance.
I think that's a good way to put it.
This has been a really illuminating deep dive. It certainly makes you think about where this could go next, considering how well these tools seem to capture complex dynamics and inform our understanding of uncertainty. What kind of new data sources, or perhaps even alternative, maybe more advanced network architectures could push the boundaries even further? How much better could we get at predicting and managing economic and financial risks down the line? Definitely something to ponder. Thanks for joining us today on the deep dive.